So yeah. So today we will go for PN junction diode. So last class we have been discussed about the what are semiconductors to semiconductors where the forbidden energy gap which may be lies between the insulator to the conductors is nothing but a semiconductors, or else you can say that here the resistivity or resistance which can lies between the conductor insulators to the conductors, which is nothing but a semiconductor. Semiconductors are two types, one is the p type and another one is the n type. The same thing we have been discussed in earlier classes. That is how the p-type semiconductor is going to be forming. Means here whenever a trivalent impurity which is added to the p-type of semiconductor, pure type of semiconductor, which is going to be forming a p-type. That means a third group of element which is added to the here either silicon or germanium, so that it is going to be forming a p-type. Majority charge carriers positive holes and minority charge carriers which are negative electrons. So these are the acceptors. So that if any neighboring atom is having an excess amount of electrons are there, if it is going to be donating that electron which is going to be here accept to form a covalent bond. Why? Because of here there is a deficiency of electrons and more number of positive holes are there. So that is the case here. So another one is that n type of semiconducting material. That means here when you add a pentavalent fifth group of element to the pure type of semiconducting material, which is going to be forming a n type semiconducting material. Here there is a majority of charge carriers are electrons and minority charge carriers are positive holes. So here which may have a excess amount of electrons are there, so that it is going to be searching that a neighboring atom is having a deficiency of electrons are there, so that it is going to donate that excess amount of electrons to form a covalent bond, so that these are the donors. Okay, majority charge carriers negative electrons, minority charge carriers positive holes. So these basics you need to know before going to discuss about the junction diode. Okay, so next. So PN junction, P-type and N-type semiconductors, which are taken separately, are of very limited use here. If we are going to be joining a P-type material to a piece of N-type semiconducting material, in such that crystal structure remains continuous at the boundaries, so that here a PN junction is going to be forming here. Next, how the PN junction is going to be functions here, which may be act like a rectifier and amplifier, a switching and other operations in electronic circuits. Rectifier means a pulsating AC which may be converted into a DC. Amplifier means whenever a low signal is there, that signal should be strengthened by this, a switching on and off and other operations. So a PN junction cannot be produced by simply pushing two pieces together, or else you don't be think that which is going to be welding like that, one to other piece. So because it gives to discontinuous across the crystal structure by doing this. So special fabrication techniques are going to be adopted to joint to form a PN junction. So what do you mean by PN junction? A PN junction is a device which may be formed by joining a P-type. Just now we already discussed that a trivalent impurity which is added to pure. Impurities are boron, aluminum, like that. Trivalent. With N-type semiconductor material. N-type means a pentavalent, fifth group of element which is added to pure type. What are the fifth group element here? Phosphorus, arsenic, like that. So these semiconductors which are separated by a thin junction, P and N. So which is going to be forming a PN junction diode, or else you need to say that a junction diode. So what is the electronic symbol? So there is a triangular shape is there. So left one is the P and right one is the N type. So here I will show you. Yeah. So this is the P type. Symbolic representation. This is N type. Is it clear? So whenever you are going to joining a P type and N type, so this is the junction diode. Okay. So structure. This is symbol representation. Structure is left hand side P type and right hand side is N type. In between them there is a depletion layer which is going to be forming. Depletion layer means that is nothing but a space charge region. Okay, depletion layer. Space charge region means here at the junction, toward the junction, there is a immobile ions which are to be present. That means there is no charge carriers which are available toward the junction. Okay. So those are going to be losing a charge and become an ions which are to be present toward the junction PN N-type regions. So in PN junction diode, N is right and P is left. And what are the majority charge carriers which are present in N region means negative electrons, whereas in P region is positive holes. What about the minority in N region which is having a positive holes and P region which is having a negative electrons? Okay. So how the depletion layer is going to be formed in between P and N type. So before that, if you are not applying any external voltage or potential difference to the junction diode by fusing with one region into the another region P to N region. So here the excess electrons in N region which may cross the junction and those are combining with the excess holes in the P region. So that here N region loses its electrons and become positively charged. And similarly, P region accepts the electrons and become negatively charged. So at one point, the migratory action is to be stopped here. Migratory means which may coming across the junction from N to P or else P to N. So that is denoted by migrated. And additional electrons from the N region which are repelled by the net negative charge of the P region. And also same thing, an additional holes from P region which are repelled by the net positive charge of the N region. So what is the net result here? There is a creation of thin layer each side of the junction here. That means which is depleted, that you can say that which is emptied of mobile charge carriers. So this is known as depletion layer. So or else space charge region. Space charge region. depletion layer. Another name is space charge region. So here, what are that? The thickness of the order of the depletion layer is 10 power minus 6 meters. Minus 6 means micro. Okay. Minus 3 is milli. 10 power minus 6. So the depletion layer contains no free and mobile charge carriers, but only a fixed and immobile ions. Its width depends upon the doping level. If you are going to do the doping is more, heavy dope, there is a thin depletion layer. If doping is less, there is a thick depletion layer. Next is the potential barrier. So the electrons in the N region have to climb the potential hill in order to reach the P region. Similarly, the electrons which are trying to cross the N region to the P region, which is experiences a retarding field of the battery and therefore which may be repelled. So the same thing is to be happened in the case of which are for small holes from P region. Next, what is the potential means? Potential thus produced, which are called potential barriers. So what is the here potential barrier for germanium means 0.3 electron volts and for silicon is 0.7 electron volts. So you can see here. So which biasing? Biasing means the current may be constituted through a component from one place to another place is nothing but a biasing. There are two types of biasings are there. One is forward and the another one is the negative reverse bias. So here left hand side is the P type doped region and which may be adjacent and joined to the N type doped region. So a potential barrier, positive and negative, is to be applied. So PN junction can basically works in two methods. A battery is connected to the diode, and the second one is the if the forward bias is in mode. So positive terminal which is connected to P, negative terminal of the battery which is connected to N is forward. What about the reverse? Negative terminal of the battery which is connected to P and positive terminal of the battery which is connected to N, which is in reverse bias. In forward bias, there should be a repulsion is to be takes place. The width of the depletion layer is going to be reduced. In reverse bias, the depletion layer width is to be increases, and here there is no conductivity. So it forces the majority charge carriers to move across the junction and decreasing the width of the depletion. So once the junction is crossed, a number of electrons and holes will recombine. For each hole is a positive and p section that combines with an electron from the n section and convert the whole is in covalent bonds which are breaks, and the electron is liberated which enters the positive terminal. Next, which is creating an electron hole pair. Electron as well as hole pair. So the current in the N region, which is carried by the electrons, and the current in the P region, which is carried by the positive poles. Next, reverse biased PN junction. If the positive terminal of the battery which is connected to N and terminal of the battery which is connected to negative terminal which is connected to P type, then that is in reverse bias. That means you need to know that the free electrons and free holes are attracted back toward the battery, so that there is no charge carriers which cannot be moved from the one region into the another region across the junction. Okay, so that in this case no current conduction. So that the free electrons and holes are attracted the back from the depletion layer, hence the depletion layer grows. So the reverse bias PN junction diode. So thus a reverse bias PN junction does not conduct any current. So only the minority carriers which may cross the junction constitute very low reverse saturation current in reverse bias. So which this current is of the order of microampere. So this is the case. Voltage current VA characteristics. The curve drawn between an x-axis voltage and y-axis current. So when it in forward bias, so the curve has which is a linear rise and the current increases with the increase in forward voltage like ordinary conductor. So above 3V, the majority charge carriers which are passing the junction and gain sufficient energy to knock out the valence electrons and raise them to conduction band. Therefore, the forward current increases sharply. What about the reverse means? Potential barrier at the junction which may be increases, and junction resistance is also increased, and okay. However, the minority carriers are which are accelerated by the reverse voltage. So which may be resulting a very thin, small current, that is reverse current in the order of microampere. Micro means 10 power minus 6. Okay. So when reverse voltage is increased, so which may be called as a breakdown voltage or the reverse current increase sharply here. So the diode which is showing zero resistance in this case, so which is known as avalanche breakdown. So reverse voltage above 25 volts, which may be destroyed the junction diode permanently. So this is the IV characteristics, current versus voltage or voltage versus current characteristics. Okay. So you need not to draw like this, starting 0. Why? Because of the current which may be conduct after 0.3 or else 0.7 electron volts. Yeah. So I am showing. So which is the reverse bias, and this is it. So the diode which may be acts as a rectifier. So as a rectifier, that means AC pulsating AC which may be converted into DC in IV characteristics. Certain current which may flows in forward bias mode, and negligible current which flows in reverse bias mode until Zener or avalanche breakdown which may happen here. Thus the PN junction diode allows the electrons flow only when P is positive. This property which may be used for the conversion of AC into DC, that is rectification. When the diode is in forward bias, the switch is closed. When it is in reverse bias, switch is open. Closed means current may flow through the circuit. Open means current doesn't allow through that. What are the advantages? No filament is necessary, which maybe occupies very lesser space in circuit, and which may operates long life. So applications of this PN junction diode is nothing but a which is a rectifier to convert a pulsating AC into a DC. Pulsating AC into DC, and also which may be act as a switch in computer circuit, and as detectors in radios to detect audio signals. Okay. Other one is that which is a as a LED to permit different colors, light emitting diode. Yeah, go for the rectification or a rectifier. A rectifier is an electrical device which may be converted in a AC, pulsating AC, alternating current. There is a fluctuations up and down, okay, which periodically reverse direction into the direct current. No fluctuations, a constant output, direct current, which may flows in only one direction. So this may be called as a rectification. So physically, rectifier takes a number of forms, including vacuum tube diodes, mercury arc valves, copper and selenium oxide rectifiers, semiconductor diodes, silicon control rectifier SCR, and other silicon based semiconductor switches. So there are two types of rectifiers. One is the half wave rectifier, another one is the full wave rectifier. Okay. A half wave rectifier, the process of removing one half cycle of the input signal, which may be established at DC level, is called half wave rectification. So, but here half wave rectification, the rectifier conducts current during positive half cycle of the input AC signal only. So AC signal means the symbolic representation. What is the symbolic representation? This is positive half cycle, negative half cycle. This is AC. AC signal means sine wave, sine wave. Okay, positive, negative, half cycle. So this is half cycle. Positive half cycle means only upper part. Negative half cycles suppressed. These. Okay. This is the circuit diagram for the half-wave rectifier. You can see AC supply. AC supply means AC. AC means input. This is the input. Positive, negative, positive. Here negative. Input signal. Okay. So this is the input voltage. This is the VM, maximum voltage. 0 to pi, 2 pi, 3 pi, 4 pi, like that. Okay. So 0 to pi and 0 to pi, the diode is conducting the current. What about the pi to 2 pi? Negative half cycle. Negative half cycle diode doesn't conduct. Okay. So that's what you can observe the diagram. So this is the primary and this is secondary. NP is greater than NS. Condition is as to fulfill. The number of turns in primary, which is greater than the number of turns in coil in secondary. Okay. So input voltage. So that in a transformer, there is a fluctuations which maybe takes place at the primary. Okay. If the signal is low, strengthen by step up transformer. If signal is high, step down transformer, you use it. Okay. So that like that, which may be here it is going to be showing like this. So the case is that here there is a constant voltage which maybe takes place at secondary. Okay now. So that whenever the signal, AC signal which may and also you need to know that here the diode which is connected in series in secondary and also load resistance RL is also to be considered. Across the load resistance only you have to take the output voltage. So here before that which is AC up to where? Here AC. Here a diode is there. After this DC. Okay. Why? Because of the diode which is converting a pulsating AC into DC. AC may be converted into DC. That is the case. So V output. So this is the current here. Maximum one. No negative half cycles are there. Input is positive or negative. Output is either you may take it as a current or else voltage. Here a half wave is to be observed here. Okay. So AC voltage across junction secondary terminals AB, which may be changes its polarities after each half cycle, positive and negative. So that during the negative half cycle, a terminal A is negative. So diode H is in reverse bias. So that diode is going to conduct any current in reverse bias? No. So current which may flows through the diode during only in positive half cycles. So in this way, the current which may flows through the load resistance RL in only in one direction. Next, what is the output frequency of half-wave rectifier? See here, 0 to pi, pi means 180 degrees. Pi to 2 pi, 360 degrees. Okay. So this is the input AC signal. Whereas in output, 0 to pi only the current RL's voltage, the frequency which is going to be showing here, maximum frequency, FM. So output frequency of half-wave rectifier which is equals to input frequency. Frequency is matched. So this means that when the AC, input AC completes one cycle, rectifier wave is also completes one cycle. Okay. So F out equals to Fn. So what are the advantages and disadvantages? So half-wave rectifier is very simple and low cost. Disadvantage means pulsating current in output contains AC components. Okay, ripples you need to say. Okay. Whose frequency which is equals to supply frequency. So that here filters are needed to remove these AC components. So the AC supply which may delivers the power during half cycle only, so output is low. So you need to calculate the half-wave rectifier, what is input voltage, at what conditions the rectifier is going to be working out, what is the input voltage, what is output voltage, what is DC voltage, what is DC current, RMS current, RMS voltage. Next, efficiency. Okay, rectification. So efficiency of the half-wave rectifier is only for 40.6, whereas the ripple factor, PAC by PDC gamma equals to. So that is not shown in this, but you need to go through that calculation part. So ripples is also 121% in the case of half rectifier. Efficiency 40.6. That means whenever a signal which may fed through the rectifier, which may not be converting a AC into a DC, only 40% of the signal which may be converting, remaining 60 gone. Okay. Ripples also, what do you mean by ripples here? Along with the DC, some of the AC components which are going to be present in the case of output section, that is called ripples. Okay. So you need to overcome this. So that's why here in place of a single diode, we are using a two diodes. So that's why here in full wave rectification, current which may flow through the load in the same direction for the both half cycles of input AC. So this can be achieved by two diodes working alternate. So one half cycle is one diodes which may supplies the current to the load, and next half cycle for another diode. And also center tap for full wave rectifier. The circuit has two diodes, D1 and D2, and a center tap transformer. So these two conditions are important. How it is working. During positive half cycle, D1 conducts. Negative half cycle, D2 does not conduct. D2 conducts. And it can be seen that current through load resistance, same direction of the both sides. So see here, two diodes are there. Here, which is this is the center tap here. Okay, diode D1 as well as diode D2. So continuous waveform is to be observed. Full wave D1 for first half cycle, second half cycle D2, other first, second, like that. Why? Because of negative half cycles does not allow through this. So full wave bridge rectifier. Next is the bridge rectifier. So which is having a 4 diodes in place of 2, arranged in the form of bridge. The main advantage of this bridge circuit is that it does not require a special center tap. The single secondary window winding, which is connected in the one side of the diode bridge network and the load to the other side. So this is the bridge rectifier. Diode D1 and D4, D3, D2. Here also full wave rectifier. Double frequency F of out. 2 diodes which are conducting. So the rectification of the full wave is 80.6 and bridge rectifier is also. Efficiency, efficiency is the 80.6. For half wave is 40, full wave is 80. Ripples are 121 in the case of 8 and half wave rectifier. Full wave rectifier, which is less than that. Okay. So that what are the advantages means it need a center tap transformer which is eliminated. Output is twice than that of the center tap. Disadvantages means it requires 4 diodes. Internal resistance voltage drop is twice than that of the center tap circuit. See here, half wave, full wave, bridge wave. How many diodes are needed here? Half wave 1, full wave 2, bridge 4. Efficiency 40.6, half wave. Full wave is 81.6, bridge is 81.2. Yeah, VDC, DC voltage, Vm by pi 2, Vm by pi 2. IDC, IDC by 2. Ripple factor, you can see here, 1.21. Whereas in full wave and bridge rectifier, only 48%. Peak inverse voltage and output frequency is also double. Transformer utilization factor. Okay, that is another one is the form factor. Peak inverse voltage, peak factor. Thank you. So this is about the PN junction diode. Okay. So with respect to the applications, we have been discussed that what is PN junction diode, what is half wave rectifier, and what is full wave rectifier. Next, another important is Zener diode. Okay. So this is the best example for the junction diode. A diode which is a specialized electronic component with 2 electrodes. One is positive, another one is the negative. That means anode and cathode. So most of the diodes which are made up of semiconductors, we know that like silicon, germanium or selenium, like that. So A means anode, K means cathode. Symbolic representation is given out. Next, Ginnar diode history. Charles Melvin Ginnar. So he was an American physicist who first described the property concerning the breakdown of electrical insulators. What is that? Breakdown of electrical insulators. So these are findings were later explored by Bell Labs in development of Ginnar diode, which was duly named after him. So Ginnar diode is a type of diode which may permits current not only in the forward direction like a normal junction diode, but also in the reverse bias. When if the voltage is larger than the breakdown voltage, that is known as Ginnar knee voltage or Ginnar voltage. So how it is appeared? Appearance is like this. Symbolic representation, Z symbol is like that. Symbol as well as Z shape is there. Okay, like this. So here the breakdown current which may flows to, but only the past the Ginnar breakdown voltage. So here the arrow head on Ginnar diode symbol points in the direction of forward current when the diode is in forward bias. The Ginnar is normally operated in reverse breakdown, and the current direction has then formed anode to cathode. Ginnar diode circuit. The most basic Ginnar diode circuit consists a single Ginnar diode and a resistor. And this may provide a reference voltage, but a series resistors must be in place to limit the current into the diode. Or else otherwise here a large amount of current which may flow through the Ginnar diode and it could be destroyed. So you can see the circuit here. Input voltage which is coming across the load and resistor which may be connected in series with the Ginnar diode. Across it the output voltage is to be considered. Input voltage is V1, output voltage is V2. So current value according to the Ohm's law, what is that? What is Ohm's law, Andy? V equals to IR. I equals to V by R. The same thing is to be. Current I equals to V by R. V means input voltage minus output voltage. The difference between the input to the output by resistor R which may gives that how much of the current which may fed through the Zener diode. That you can easily calculate. So the value of the resistor which may be calculated to give required value of current for the supply voltage is used. So forward bias. See, the B means battery circuit diagram. A means anode, positive. P type, not positive. P type consists positive holes. N type consists negative electrons. So when a Zener diode is in forward bias, it is operated like a normal junction diode. That means forward means p-type p-type material which is connected to the positive terminal of the battery, and the negative terminal, negative side, N side, which is connected to the negative terminal of the battery. So that means which is in forward bias. That means charge carriers which may easily flow from the one region into the another region across the junction. Why? Because of there is a repulsive forces to be takes place between them. So the electrons or holes which are swept across the junction in a large current which may flows through this Zener diode. So that is also to be observed in the case of junction diode. That's why this may be works as a normal diode in the case of forward bias. Reverse bias. You can see here the current is 0. But at a certain voltage, the which called the Zener voltage, the current value increases sharply. So here each Zener diode has a breakdown rating which may be specifying that maximum voltage that can be dropped across this Zener diode. So reverse bias means negative terminal which is connected to cathode, positive terminal of the battery which is connected to anode. Okay. Actually, it may be that is wrong here circuit. Why? Because of here. See, this is wrong. Why? Because of Zener. Sorry. Like that. Here is down. So characteristics, VI characteristics, forward bias. There is the same as that of the ordinary. If voltage increases, current is also increases. Forward bias. Whereas in reverse bias, there is a small leakage current between the 0 volts and the Zener voltage. That is a tiny amount of current which may be able to flow. That is due to the minority charge carriers. That means when the voltage which is reaching the breakdown voltage VZ, suddenly current which may flow through it. So VZ means here VZ, reverse voltage. This is the reverse conduction. This is the breakdown voltage. At a time, simultaneously the current which may flow through it. So the reverse voltage increases, the leakage current remains essential constant until the breakdown voltage reached. Forward region, reverse region, Zener breakdown region. A Zener breakdown. The Jenner effect is a type of electrical breakdown in reverse bias PN junction diode, which the electric field enables tunneling of electrons from the valence to the conduction band of a semiconductor, which may be leading at a large number of free minority, not majority. Minority. Why? Because of majority, which is attracting towards the battery. Only minority which may flows. Minority means N-type minority is positive holes. P-type minority is negative electrons. So that due to this only, the suddenly increase the reverse current. This is the electron pulled out their covalent bond because high intensity of electric field. Basic parameters of Jenner diode. So Jenner voltage must be specified. The most common range of Jenner voltage is 3.3 volts to 7.75 volts. And a tolerance of specified voltage must be stated. While the most popular tolerance are 5% and 10%. And the precision tolerance is low, 0.05%. A test current, IZ, Jenner current, must be specified with this voltage and tolerance. So the power handling capability must be specified for the Jenner diode. Popular power ranges are 1/4, 1/2, 1, 5, 10, like that. Applications are which may be acts like a Jenner regulator, Jenner comparator, Jenner limiter in power supplies. Okay. So Jenner diode, which is the best example for the PN junction diode. Okay. So and also which may be used in reverse bias condition. Jenner diode. So which is the best example for the junction diode. This may be works in reverse bias condition. The example where you are using means in stabilizers. There we are using in reverse bias condition. Whenever the high voltage or voltage fluctuations are to be takes place, the stabilizer which doesn't allow any current through that because of this component, okay, which is connected in reverse bias in the circuit. That's why immediately the stabilizer warn you that here it does not allow the current or voltage through that. It stops that. That's why it is the Jenner diode works in a reverse bias condition. So this is about our today's class about the PN junction diode, half wave rectifier, full wave rectifier, and finally Jenner diode. And tomorrow's class is very, very important. Why? Because of here, we have to discuss about the BJT, bipolar junction transistor. Okay. So what do you mean by transistor? And how types of the transistors? What is NPN and what is PNP transistor? I will show you through the slides. I will explain through the slides. Okay. So, right, all the best. Right, thank you.